Okay, so I'm going to start right now, for those of you guys watching the video, with the idea of these skills journal questions. And what we're going to do is we're going to graph just a normal function. Then we're going to graph the function, but everywhere we see x, we're going to put x plus 2. We're going to try it again, but everywhere we see x, we're going to put 3x, and then negative x. So help me out, though. What is the function number 7? What is the actual equation? Okay, so let's graph this first one. Pretty straightforward. Go to the y equals screen. Type in 2 bracket x minus 1 all squared. And before I even type it in, I should know roughly what it looks like, right? It's quadratic. Smiley face parabola. How many roots is it going to have?
1.
And what's special about that one root? It's one of those double multiple roots, right? Because really this is x minus 1 next to another x minus 1. So when I do my zoom and I graph the thing, I'm expecting it to just barely touch the axis, right? And it looks, it has the x-intercept right there at 1. So hopefully you guys can, in the meantime, kind of find some other points and find me the y-intercept and find the x-intercept. Does that all make sense so far? Okay, let's try the next one. What I'm going to do, though, is that the purpose behind this activity is I want to show you the similarities in these graphs, because today's topic, if you guys haven't looked at this yet, is going to be called horizontal and vertical translations. And I want to talk about different ways that we can transform graphs. So the next couple of days are going to be about translations, stretches, and reflections. And we're going to talk about how these things work. So let me go back here again. This next one here, f of x plus 2. I'm going to retype the exact same equation, 2 bracket, but everywhere you see x, put in x plus 2. So I'm just going to put in an extra x plus 2 right here, and then I'll just keep going. So this x right here is now x plus 2. I still have to subtract 1, and then I have to square it. Now, if you wanted to, you could do some simplifying here, but I'm not going to bother with the simplifying. Did you guys get what I just did there, though? This x that was right here is now x plus 2. And while I'm at it, I'm going to write the other ones in, and I'll get to them later. So 2 bracket, rather than writing x, though, now I'm going to write 3x. Keep going, while then still subtract 1, and square the whole thing. And then for the last one, it's 2 bracket, but rather than writing x, we're going to write negative x. Still have to subtract 1 and square. What I'd like to do is, one at a time, compare how these functions go together. And hopefully this will be a learning opportunity that we can use to merge into our first set of notes for the day. So, I'm just going to turn off the third and fourth ones, though, and just compare them one at a time. You guys with me so far? Let's compare the original graph to the graph that has an x plus 2 in its face. Let's see how they look. Okay. Do you guys know how you can make the graph like a thicker or a bolded line, just so you can kind of tell the difference between the two? Here's like a bolded line graph, and here's like a regular line graph. You guys able to do that if you need to? Let's talk about this parabola. The bolded one is the first one. The thinner one is the second one. Today's topic, by the way, is horizontal and vertical translations. What's a translation? If I ask you to translate something in English to French, I don't know if that's really what we're talking about, right? What would a translation mean in a math context? Yeah, it'd be like sliding something over. Can you guys visualize how this bolded graph right here has the exact same sort of shapeness to it as this other graph over here, except it's been slid over? You guys see how that works? Keep that in mind, okay? Now, we're only going to do these one at a time in terms of these lessons, but the lesson we're going to do after translations, which we'll do tomorrow, is on, look at this, what is it? Is then going to be on reflections and stretches. Watch this. Let's do the next one here. So let's turn this one off, And let's turn this one on and compare. Here's our first parabola. And this next one is in there. You see how this is the first one right here, and that one's sitting inside there like that. I want to show you something real quick here in terms of intercepts. You know how the intercept for this one right here was at 1? I'm going to try to find the intercept for the other one by just finding the minimum value on it. You'll never graph. Look where the minimum value of the other one is at. It's at 0.3 repeating. What's 0.3 repeating as a fraction? 1/3. You know how when we wrote this equation here, we did a, we put a 3 right here? That can't be a coincidence. There's a 3 right here, and our x-intercept went from being 1 to 1/3. I'm going to show you the link a little bit later. Okay. I want to show you some other links here. Let me go back to the one that I did earlier here. Okay, here's our first one, and then here's the second one. What's the intercept of the first one? It was at 1, right? Where is it on the other one right there? -1. How far is it from 1 to -1 in terms of distance? 2. That's weird. X plus 2. Maybe there's a link there. Anyone here? And then we do the last one. Tomorrow's topic is reflections and stretches. So I did the first one and the fourth one. Hopefully you'll see that here's the first one, and here's the second one. It's actually been reflected. Imagine there's a mirror. And what we've done is we've actually flipped it side by side. You kind of visualize how this one right here flipped over a mirror to over there. Can you see how that works? So that's my goal over the next little while, is I want to show you the link between the idea of putting something inside a function like the x plus 2 or the 3x and the minus x, and some basic rules about what it would do to a graph. Does that make sense? So let me start my notes here now, and hopefully I can make this, I hope I can do an even better job of kind of explaining these links. So today's concept is going to be translations, and then tomorrow we're going to get into stretches and reflections. And all of these are basically the idea of, if you have a function, a graph, how can I kind of like twist it and warp it and flip it and slide it around to try to get it to like move to a different location, if that makes sense? And we're going to talk about some rules that we've discovered that kind of cause it to do that. And the cool thing is that these rules, they actually apply to all kinds of functions. So my first slide here talks about how, you guys know linear and quadratic functions. We've done those ones before, but these rules that we're going to learn, they actually apply to the exponential functions we learn next unit, the sinusoidal functions we learn eventually. So these are actually some all-encompassing rules that we're going to talk about. Let's compare these graphs then. Just going to graph them real quick. This is basically the same activity we just did. Clear all this out. If I give you x to the power of 3 as the first graph, you guys know what that looks like. It's got that just like the basic, pattern to it. So far, so good. Well, let's try the second one. Do it on the same graph. Go bracket x minus 1, cube the thing, and then add 3, and see what that looks like. It's kind of tricky to see, but can you guys see how it kind of has moved up to there? And maybe I should just do them one at a time, actually. Maybe doing both on the same graph doesn't work as well. You guys see how that little twist, you know how the little twist point right here used to be right about there? And now it's like more like that little twist happened right there. I want to show you something. This graph has actually been moved over and up. And the distance that's been moved over is 1 unit over and 3 units up. This is actually the exact same graph, just been translated over and up. Makes sense though? I want to try to explain to you these rules then, and what we've discovered in terms of how making these subtle little tweaks like this -1 and how this +3, how it can affect the graph. So here's the rules first. I found that often it just works best just to show kids like how these rules work, and then I'm going to try to explain them better. And I actually have what I think is a pretty good metaphor for how this works using a vending machine again. Actually, I've already used the vending machine one before. So let's talk about a vertical translation. If you were to take a function and you were to add a number afterwards, you know what it does to the function? Is it moves the graph up. They'd be considered congruent to each other. You guys know what congruent means? Like the same size and shape, just in different locations. Like that chair is congruent to that chair. They're just in different locations. So it's like congruent would be the same size and shape. So if you were to add a number afterwards, what it does is it moves it up or down depending on whether the number is positive or negative. See how this one right here was just x to the 3? And then I have +3 kind of sitting way at the back of the function there. You know what that +3 did to the graph is it moved it up 3. Watch this. What if I were to take that same function and change this +3 and make it -3? What's that going to do to the graph then? Down, yeah. That little twisty piece should now be down here. So if you want to move a graph up or down, but like have it have the same shape to it, all you have to do is just add a number after the function. Now I'm going to hit on this terminology a lot today. It's actually fortunate for the kids who aren't here, because it's such an important day. It's the idea of whether something is inside or outside of the function. Can you guys see how right here, this is what my previous function used to be, and then after I'm done, I'm adding a number. I would consider that to be outside of the function. Because I want to compare this now to the horizontal translations. Can you guys skip to this slide? Sorry, I'm jumping around here. A horizontal translation, what you do is you add or subtract a number, but you do it inside of the function. You know how you take the one function and you put it inside of another one? If you do that, you discover that moves things left or right. Okay? Now, how does it work here? If the number is positive, it moves it one way, and if it's negative, it moves it the other way. So let's just do a quick little test here. See how I have an x -1 right here? Can you guys agree how that's kind of like inside the bracketed function? Well, what that did is it took the graph and it slid it that way. But here's where kids get really confused. This formula right here already has a negative. The formula already has a negative. So if the h value is positive, then the negative makes this positive stay negative. So like, long story short, this thing right here moves it to the right if it has a net negative. Here's the other way. You guys know how there's a difference between a factor and a root? And a factor would be like x -2, but the root is actually 2. Think of it in that sort of terms here. This h value right here is the actual root. So if the root is 2, you know how 2 would go on a graph right there, that's where 2 would go. You slide it that way too. However, it's going to get written as x -2 to do that. X -2 actually slides it towards positive 2. We'll get there. What is x +1 going to do then? If I gave you an x +1 as a factor, what's the root? Yeah, which takes the graph and then slides it into the negatives. So watch the same graph right here. What if I were to play around with it and now make this x +1? X +1 would have a root of, like, say, -1, which really takes graphs and moves them into the negatives. So +1 takes this graph and moves that little twisty section that way. Maybe how that works? So we actually have some rules that we can use then to describe how these work. I put a little note here. Horizontal translations seem like they should be opposite. Because if you have a plus number, you actually go into the negatives. And if you have a negative number, you're actually going into the positives. Kind of like with factors versus roots, right? X plus 2 has a root of minus 2. X minus 2 has a root of plus 2. Let me give you my analogy. So I want to talk about inside or outside of the functions. Give me an equation to work with here. Let's use this one. Here's my analogy. Here's your normal function. Your normal function is to cube a number. That's like normally what you're supposed to do. So if I give you the number 1 as my input, what's your output supposed to be? 1. Because 1 cubed is 1. What if 2 is your input value? Your output value would be 8. Now, 3 would give you 27, 4 would give you 81. You guys okay with that? And what we want to do is we want to consider ways to make slight tweaks to the function either before or after you finish. Right? So, let's just go here real quick. Let's talk about what happens after you finish. Let's say that I were to write out the function x cubed, but then after I'm done, add 3. I'll just write it so we can see this as well. X cubed. But can you guys see how like the plus 3 is like, well, after the function? This is going to take an entire graph and move it up. Maybe here's the explanation. Think of it as like a vending machine kind of concept. If I plug in 1, I'm supposed to get back 1. But this is kind of cool. After it comes out, the vending machine's busted. And so I'm supposed to get back 1 chocolate bar. I put in $1, I get back one chocolate bar. However, the plus 3 afterwards means the machine's broken, and I always get 3 more than I'm supposed to. So if I plug in 1, I'm supposed to get back 1, but actually I get back 4. Because when I'm done, I get 3 more. So you plug in 2. 2 is supposed to give you 8. So I don't know, in the example here, you plug in $2, you're supposed to get back 8 chocolate bars. But regardless of what you put in, you always get 3 more than normal. So 2 wouldn't give you 8. 2 would now give you 11. Because everybody, regardless of what they put in, gets like a bonus plus 3. Does that make sense? You can see how that's like an after the function? This is what you were supposed to get, but now you're getting 3 extra ones. Well, all that does is it takes a graph that normally would look like this, and this is kind of where I lose my board here. It takes the entire graph, select, there it is. Hang on a second. What am I doing? I have 2 different colors. Have a graph. The graph normally goes here. And because the plus 3 is after the function is over, all of your y values are now 3 higher. So all it does is it takes your graph and just moves everything up 3. This guy, when he put in $0, was supposed to get back 0. But the cool thing is this machine gives everybody 3 more than they're supposed to get. So he actually gets to go up and get 3.
Aurora, Chief Body, please come to the
1
office.
was supposed to give you 1 right here, but it goes up 3 more as well. Like literally everything goes up 3. If this thing right here was a minus sign, what would that do to the graph? It would just drag the whole thing down 3. Maybe there's an analogy for that. Taxes. I'm supposed to go to work. I work for 1 hour. I earn $1. Okay, again, keep in mind this analogy is not perfect, right? But I go to work for 1 hour. I earn $1. And then the man comes and says, I need $3 from you after you're done. So what do I got to do? Well, for my $1, I got to give him back 3. So now I'm down 2. Does that make sense? And he does this irregardless of how much you make. This is like a flat rate, you know what I mean? So even if I was supposed to make $1 million, still got to pay back your 3. Supposed to make $10 million? No, you're down to 999,997 or whatever it is. You know what I'm saying there? So that's an after the function kind of concept, where after you're done, you have to drag the graph down. Does that make sense? Let's do a couple more examples that fit that on random slides that I've missed here. Let's try this one right here. So the goal that I'm trying to show you here is how to kind of save some time and know what graphs look like without even needing to graph them. I know what an x squared graph looks like. I mean, it's just your standard parabola, right? So don't even grab the graphing calculator. x squared graph looks, give or take like that, right? That's your x squared graph. But I shouldn't need a graphing calculator to know what x squared plus 3 looks like now. Because what is the plus 3 going to do to it? Regardless of your input, everybody's going up 3. Suppose you're supposed to get 4, nope, you're getting 7. Suppose you're supposed to get 5, nope, you're getting 8. Right? Every single one of these points. This point right here is now up 3. This point is up 3. This point is up 3. Everything is up 3. This vertex that would have been at 0, 0, well, now it's at 3. And so everything now gets to be 3 higher. The graph still has the same shape though. It still has the same congruency. Does that make sense? All you're doing is you're sliding the graph up or down. Does that make sense? So for things that are outside of the function, consider what you would do to the y value after you're done. Let's do a couple more rounds. What would this guy right here do? You're going down 6. This guy right here. Anybody else get that? Yeah, let's talk next to. Kind of messing around with you right here. If your graph is supposed to be the old function down 6 or plus 3, but look what I did here. I put the minus 4. You see how I put the minus 4 kind of on the wrong side? This answer is going to be up 4. And maybe here's the best way of showing you why it's up 4. See how I don't really have y by itself right now? If I were to add 4 to the other side, look, now here's my function, but now up 4. And then this one right here, it's now my function, but down 2. So you may actually be asked how to do this, and they might throw like the plus or minus sign on the other side of the equation. So you do have to have your function in a normal sort of spot, and the plus or minus sign has to actually be right behind it. Or if it's on the other side of the equation, just move it over. Sound good? Okay, so let's talk more about horizontal translations then. Let's make up another example here. Let's use a quadratic for this one here. Let's do x squared. Let's say x squared was your normal function. So I don't know, whatever the scenario is, if you start with $0, you get 0 chocolate bars. $1 would give you 1 chocolate bar, $2 would give you 4 chocolate bars, $3 would give you 9. We're good so far? Here's how this would look. If I put something inside the function, it would now be like, say, x minus 1 squared. So I'm kind of putting it before the squared sign. I'm not talking about it over here. This would move it up, but this should be moving it side to side. That makes sense. But it's backwards. Okay? Because what ends up happening is x minus 1 would actually move it that way. I'm actually pointing to the right, by the way, if you guys are watching the video later. I'm pointing to the right, I'm moving to the right. And here's one reason why. Isn't x minus 1, isn't that a factor which has a root of 1? Right? So we've already kind of gotten used to that idea of things going backwards, but I have an even better analogy. Okay? This is actually before you get to the vending machine. So in my previous example, after the vending machine was done, it gives you 3 bonus ones. Well, in this example right here, you're being robbed. Before you go to the vending machine, here's how this works. You normally are supposed to come with, say, $5. Right? What would $5 have gotten you? Well, $5 would have gotten you 25. Right? 5 would have turned into 25. But there's a bully waiting for you at the vending machine. And the bully, every single person, before he puts his money in, the bully says, give me $1. You know what I'm saying here? So even though you came with $5, how much actually goes into the vending machine? 4. Which means that rather than getting the $25 that you were hoping to get, you're only getting 16. Not 24. See the difference here? If I put the minus 1 after the function, you would have got 25, and then the guy steals 1. See how it's much worse for the guy to steal the $1 from you before you begin? If you started with 5, you were going to get 25. And then if you had to lose 1 from 25 after the function, yeah, no big deal, you're going to have 24. But this is different. This is before you get to square your money, before you even go, then it gets taken away. So your 5 becomes 4, then you get to square it, So then you only have 16. You know what I'm saying? Now here's where my logic comes in here. Let's say that this happens to everybody, right? Because regardless of whether you're plugging in 5 or 6 or 7 or 8, everybody knows they're losing $1. Right? Now, you as a, I don't know, this analogy is not fantastic, but I think it works fairly. You as a worker know that you want to earn $100. Right? You know you need to take home $100. How much money should you bring? No, because that's not how this function works. This function steals money from you before you start. You should bring 11. Because you know you're going to get robbed, right? So if you want to have 100, bring 11, so that 11 drops down to 10, and then your 10 becomes 100. Right? Because if you come with 10, expecting that 10 will become 100, you're only going to get 81, because your 10 will drop down to 9, you square the 9, and then you'll have a deficit. So you need to intentionally bring an extra $1. Well, here's what that does to the graph. If you have a -1 in your graph, it slides the graph towards the right because you actually need to bring an extra $1. You need to go over to the right more, $1, to get the same output you were hoping to have. Does that make sense? So if I were to draw a graph right here, so that I can do this nicely, and normally the graph would have looked like this. Let's pick a number that's not so big. Let's pick the number 9. If you wanted to get an output of 9, normally you better bring 3, right? But under the new function, if you want to get an output of 9, how much better you bring? Better you bring. How much should you bring? 4, right? Because you know you're losing your $1 before you start. And so now it has to be 4.9. You know what that does to this point? This point that used to be over here at 3.9 has now slid over here to 4.9, and it slid your graph that way. Does that logic make sense? So once you wrap your head around it, you just need to write down some rules. Okay? And if you understand these rules, it's actually pretty straightforward. So without even looking at this, which way is the graph going to slide? Is this quadratic graph, that is the ugliest quadratic graph in the world, is this quadratic graph going to slide towards the left or towards the right? Towards the right, which seems backwards, because you see a minus sign, and the minus sign makes kids think, well, I better go towards the negatives. But that's not the case. It actually is going to slide towards the positive. So 2 reasons why. Right off the bat, don't we know that if this is a factor, the root is kind of the opposite of that? We've already done that logic. But if that doesn't make sense, think of it this way. This function is asking you to subtract 3 before you start. So let's say you want to get this output right here. This is the output you're hoping for. Well, if you're supposed to subtract 3 before you start, you better bring 1, 2, 3 more dollars, because in this example, the bully is stealing from you before you begin. And so that point then slides over 3. So you better bring, you understand? If none of that makes sense, all I need you to do is memorize 4 rules. Add something after a function, slide it up. Subtract something after the function, slide it down. This is the bully stealing from you after you put your money in the machine and you do whatever it does. If it's an inside the machine kind of concept, it slides left or right. If it's a negative, ultimately, you're sliding it to the right. If it's a positive, slide it to the left. So let's try some more examples. What's going to happen here? This x minus 6 is going to slide to the, this x plus 3 is going to slide to the, that makes sense? Okay, so one of the things you might be asked to do then is take a look at 2 graphs and tell me how did they get moved. Now, what I don't need you to do is write me the equation of the graph. I just need you to tell me how the graph was moved around. So let me do the first one for you. Let's call this graph f of x. I don't actually know its equation. I mean, I'm sure I could maybe try to piece together what it is. It's an absolute value, something or other, but don't worry about that. Let's just talk about how it got moved. In words, how did it get from here over to here? What happened? How far did it slide? 3. Now, since it went that way, which is to the right, you would write this as f of x plus, no, not plus, minus 3. That's how we would notate it. You see how this kind of links back to where we started our year? Really, all you're doing is all of your x's are now being replaced by x minus 3's. And if you do that, it slides the graph positively. So let's try this one over here. Let's call this one g of x just to keep them separate. How do we get from the top graph down to the bottom graph? Has to slide down 2, right? How do you notate that in math jargon? Do I close the bracket or do I write it inside the bracket? Close the bracket first and then subtract 2. This is after we're done with the function, then we pull 2 off. See the difference? One, you're getting robbed before you even put your money in the machine. The other one, you're getting robbed after your money goes in the machine. There's a difference, right? This is actually one of the reasons why on your first assignment, there was a question where I had you guys figure out which one was better, whether to have your like 29% deduction of tax before you take out $200 or after. Does that make sense? This is the exact same concept here. One of these, we're applying our function afterwards. And one of these, we're applying a new function before. You know what I'm saying? One of them slides the graph down, one of them slides side to side. We can do both at the same time, by the way. You can slide something up and over, down and left. So, use the vertex to kind of figure out. This one's going up 1 and backwards 2. So why don't we label this as like h of x? If that's h of x, what's the second one? Do we need a plus or a minus inside this to slide it? I mean, once you memorize these rules, it's pretty straightforward. If you need to, write them on your combination. So we need to add a number. How far do we need to slide it over? Looks like 2, I think. Well, that would get it over to right about here. What needs to come afterwards? Okay. F, G, H, I, whatever. It's a letter. You guys want to take a stab at this one? What would it be? So you said x minus 1? I think it's minus 1. Because this minus 1 right here slides it over that way one. The minus 1 afterwards slides it down. Oh, yeah, okay, yeah, so then we actually need to make it x. Yeah, x minus 1, minus 1. The minus inside the brackets slides it opposite of what you'd think. You'd think a minus would make it go further negative, but it makes it positive. It's inside the function. The minus 1 afterwards slides it down. Agreement? Awesome. Okay, so let's try this one here then. Describe for me in words what's happening in this translation. We have a function. I don't even care which one it is. It could be linear, quadratic, cubic. And we're throwing an x plus 2 inside the brackets. And then we're throwing a plus 9 outside the brackets. In words, what's it going to do? Where's it going? Yeah, left 2, up 9. A lot of teachers, when they teach Math 30-1, they actually start with transformations. And I don't. The reason why is I want to give you guys a little bit of practice work using linears and quadratics and quartics, again, that sort of stuff, before we get to this. But the reason why some teachers do this first is because these rules apply to every type of function that we're going to learn about in the course. If you replace all of your x's with x plus 2's, it slides the graph over 2. If you throw a plus 5 at the end, it moves the graph up 5. So what I want to do here is an activity where we'll use some functions that we've done before, and I want to rewrite them with these two transformations of sliding to the left and up 9. Some of them you'll recognize because we used these graphs before. But other ones we can still do this with. You don't know what a log is yet or what a sine is yet, but you can still do this task. Let me do the first one for you. What this means to do here is do x plus 2, then square it, and add 9. Does that make sense? The main function is x squared. So inside the function, replace your x with an x plus 2. And then when you're done, throw in a plus 9. What would this do to the graph? Left 2 up 9. Well, what about the cubic function? Well, the basic function is to cube something. But rather than writing x, we're now writing x plus 2 inside the cubic part. And then when we're done, well afterwards, throw in a plus 9. Makes sense? Well, we can do this for all of the other functions we're going to learn about this year. So next year, we're going to talk about a square root function. Well, what would this look like if we wanted to move it? It would look like the square root. Well, it's supposed to be x, but all of our x's now are x plus 2. And then after we're done, meaning outside of the square root sign, 1 over x. It was supposed to be 1 over x. X now becomes x plus 2. Stop your fraction. We're done with that bit of it. Add 9. You guys can get how this looks? Alright, so this will be the absolute value of x plus 2, then plus 9. This will be the log. You don't even know what a log is yet. Who cares? You can still do this. It will be the log of x plus 2. And then after we're doing whatever a log is, we will then add 9. 2 goes to the power of x. Well, rather than write it to the power of x, it's now to the power of x plus 2. Stop with all your exponent stuff. When you're done, add 9. How this works now? Okay, this next one here is a bit more of a challenge then. What happens if I have more than 1x? What happens if I have more than 1x? What does this notation right here mean? F bracket x plus 2. It means that everywhere you used to have x, put an x plus 2. So it used to be x squared, it's now going to be x plus 2 squared. It used to be plus 3x. It'll now be bracket x plus 2. There used to be a plus 6. I'm now done writing the original function. So this is me plugging in my money, and I've gotten back what I'm supposed to. Except, remember how I get like that bonus $9 when I'm done? Now that I'm done, throw on an extra plus 9. What could we do in a function like this? I'm not going to make this do it, but what could you do? Right, like you can put the 6 and a 9 together, right? You could distribute this stuff here, you could FOIL that stuff out. If you wanted to, you could, right? But all that's going to happen is this graph, wherever this graph was, it used to be some sort of quadratic, it's now going to be moved left 2, and then up next. Okay, 2 more. Sine x then, it would turn into sine of x plus 2, and 9. Okay, you guys try the last one. I'm going a little nuts on the last one just to see if you get the concept of it. Try this one last one here without me doing it for you. Does anybody have any clue what this graph is going to look like? I don't care. What's the new graph going to look like? It will look exactly like the old graph, just slid 2 and up 9. That's what it would be. Everywhere you used to have an x, so here, here, there, and there, all of those x's, I just wrote x plus 2. And I wrote them all in brackets, because I may need to distribute or something like that, so I may as well be diligent and put them all in brackets. And then when I was done it all, that's it. I don't care what this graph looks like. This graph could have been a happy face, for all that mattered. Because what's going to happen to that graph, I feel like I'm being really redundant, but hopefully it's the point. It's going to go over 2. That over 2 would take it to there. And then the plus 9 would move everything. So good? Cool. All right, let's move on. Okay, this is a slide here kind of talking about how we've actually learned about this before a little bit. In quadratics in grade 11, we would have learned about something called vertex form. And if you wrote it in this format, we haven't done this in a long time, but I just want to point out, in case you remember this, that this actually helped you find the vertex, this h and k number. And we just learned it last year that just whatever this guy right here was, you take the opposite of it. Like, you know, if this was positive, you make a negative. If this was negative, you make a positive. So we actually have kind of learned about this concept before. If I were to give you the graph of y equals 3x minus 2 squared plus 3, I know where the vertex is. The vertex is at 2 and 3. Because all we do is we just take this number right here, flip its sign around, so I make negative positive, and then 3. The reason why is that a regular x squared graph has just been shifted over and up, that's all. We actually have learned about this, we just didn't know it yet, I guess. Okay, let's try some other tasks. Once you get the hang of these 4 rules, I need to show you how to apply it to all sorts of new and unique situations. And this is where it's hard for me as a teacher because I don't know how they're going to test you on this in the diploma. But I've now taught you the concept. Like, I think you all get the idea. A plus number afterwards moves it up. A minus number afterwards moves it down. Right? As soon as you know these 4 rules are good, I need to show you different ways in which they might test you on it. Sound good? So here's the first one. What I might do is I might give you some tables of values here. So I'm just going to give you some random points. And then what we're going to do is we're going to figure out where those points moved to after this transformation. So let's plot them one at a time. Negative 2 and 5 would have been here. Negative 2, 5 would have been there. Where's it going to move to, according to this transformation? After the transformation, where's it going to be? Over 2, up 1. So what's the new coordinate? If you go over 2, the negative 2 now becomes 0. If you go up 1, the 5 will become a 6. Let's try another one. I'm not even going to plot 0, 0. Let's see if we can do it without plotting it. 0, 0 needs to go over 2, up 1. So the over 2 would take the x number and make it go from 0 to 2. The up 1 would make the number go from 0 to 1. 2, 4. Where's it going now? Yep. 4 to 5. 3 2s going to 5, 3. I don't even know what the function is. And this is actually one of the things that they use on the diploma to try to make sure you really know what you're doing, is I didn't even give you something you can graph. I just give you some random points. And I said, well, where would these random points move to? You know what I mean? Here's another option. They don't have the ability to test that you can actually draw a new function because there's no written response. But I have seen a question before where they gave you a function, they gave you just a random little snippet of graph. It wasn't even a full graph. It was just like a little piece like these ones are here. And what they basically did is they gave you a couple of choices and they say, well, where would it move to? And they showed you like 4 pictures of a graph. And then you had to tell me which picture is the one that it would actually move to. You know what I'm saying here? So why don't we just try 2 of these? I don't want to do all 4 because I think you get the idea here. Where would this graph right here move to if you had this notation here? What would it look like? Hopefully, you'd be able to figure out that it would look like that. Any agreement on how that works? Basically, just slide the whole graph over 1. And so what they might have done is part A, they would have like maybe slid the graph over to there. B, they would have put it in the right spot. Maybe C, they would have put it like down. D, they might have flipped it upside down because we're going to learn about flipping graphs later. And so you have to figure out which one would be the correct one. Let's do number 4. Just because number 4 has a nice little twist on it. What am I trying to hint at for number 4 here? What's the twist? Does this make sense to you guys? Alright, so bring it to the other side. So all this means is take the graph, move it backwards 1, or over 1 and down 2. So over 1, down 2, over 1, down 2, over 1, down 2. It means this should look roughly like that. All I did is I just found a couple random points to use and just connected the dots. You see how that could be a possible test question? They'll just give you a snippet of graph and ask you where did the graph move to according to these conditions. You can't type it in your graphing calculator because you don't really know what this graph even is. You just know what this notation means. What do we got left? One last example. Okay, last one. The be all and end all. The big one. I saw this one year, and this was a numeric response question. And it was nasty because, I mean, first of all, you can't really guess and check on numeric response questions. Like sometimes on multiple choice, you take the 4 answers and kind of bump them back in to the original equation. This one's kind of neat because it's really combining everything we've done so far. We're going to need to write ourselves an equation. We're then going to transform the equation, and then after we're done, then we're going to try to figure out what the y-intercept happens to be. So let's take it piece by piece. Let's say I told you that you had a function that has roots of -2 and 3. What does that mean? I'm going to use that to write myself an equation like y equals something if I know the root is -2. So that's good. But what are we missing? Missing that leading coefficient again. So to find the leading coefficient, I plug in 1 for x and -12 for y, and I try to find that leading coefficient. So -12 equals a, that'll give you a 3, that'll give you a -2. Let me know if I lose you. Finding out that a is 2. Okay, so it means I have a function y equals 2, x plus 2, x minus 3. However, it then says that my function undergoes the transformation f x plus 4. What's that going to do to my graph? Slide it 4 units left or right? Left. But you know, another way that this notation can be interpreted is this just really means everywhere I used to have an x, I now write in x plus 4. That makes sense? Because that's also what this notation means. You can take it as a slide it 4 to the left notation, but it also means everywhere you used to have x, write x plus 4. So now let's write 2 bracket x plus 4 plus 2. And then rather than writing this as an x, write it as x plus 4 minus 3. Well, that's actually going to give you y plus 6, and it's going to give you y plus 1. Actually, that makes a lot of sense, though. What were my old intercepts? -2 and +3. Okay? If I were to just kind of imagine what the old graph looked like, the old graph had an x-intercept at -2, and it had an x-intercept at 3. That's what the old graph did, right? But according to my new graph, I now have an x-intercept at -6 and an x-intercept at -1. Well, how did that happen? Well, look, this guy got shifted over by 4. This one got shifted over by 4. Isn't that what we said was going to happen when you use the x plus 4 notation? Doesn't it shift everything to the left by 4? 60 fitting. So the only thing I have left to do is now take this guy right here and figure out what my y-intercept is going to be. Now, I could FOIL the whole thing, or I could recognize the y-intercept is going to be the product of 3 numbers. The 6 will times by the 1 to give you a 6, and then at some point later, the 2 is going to get distributed in. So if you distribute the 2 in as well, your constant term is going to be, this should be on a diploma. Numeric response. It's nasty, eh? It's actually not that bad if I can prep you for it, but this is my struggle, is individually, hopefully you guys would agree, I've shown you all those skills up till this moment, right? You guys know what the x plus 1 notation means. You know how to make an equation, but putting it all together, I can't know exactly what they're going to ask of you. You have to have like all these skills in your toolbox. Sometimes I talk with my kids in 30-1 about how I like to approach the analogy of it being like a toolbox. Sometimes you need to be able to use a hammer, sometimes you need duct tape, sometimes you need WD-40, right? And all of these things can be used to solve the simple problem of height not working. You can bang away at it. For some kids, that means that you like guess and check answers. That's a possibility. You could use your graphing calculator. That's using duct tape, fixing it together. Some kids, they use other methods. So I need you guys to have lots of different tools at your disposal so that depending on the question you're given, you're like, oh yeah, I've done this little section before. If that makes sense. Okay. Let the lesson go. Did that make after this morning, and what did I always say? I always say that makes sense all the time. Now I'm so self-conscious of it. But did that make sense? Yeah. Oh, it is a little loud. Do you even notice that? Yeah. There's certain things I say all the time. I know, did that make sense? I say that a lot. I steal your pencils all the time. It's never me-ism. I steal the pencils. Yeah. I don't actually bring pencils around. I just snag them out of their hands instead. If you do that, by the way, don't take their pencil back with you and then start chewing on it.
Okay.
Yeah, that's actually not good. Also, learning experiences I've had as a teacher over the years. Okay, you guys are okay for now? Yeah. Okay, cool. We got 15 minutes left, so do what you want in the last 15. We are going to do a lesson tomorrow. It's kind of the second half of this lesson. What I want to talk about tomorrow now is the idea of what if we throw in two functions, things like, where do I got a good one? What if I throw in some negative signs? What if I throw in, let's see, there's some negatives. What if I throw like a -3 in front of the function? What if I throw a -1,4 in front of the function? Or what if I throw like a 2 inside the function? What we'll discover is that it also does certain things to graphs. Okay, why don't I stop though?